It's smaller than a mosquito bite, yet somehow it hurts far more. A single sheet of paper, a single thin line of pure pain. The wound barely bleeds. Sometimes you cannot even see it at all. But your fingertip screams like you just touched a red-hot stove. Some paper cuts never even reach the deepest layers of skin. So how does something this tiny deliver such enormous, lingering agony? Your hands are the most sensitive precision tools your entire body owns. The finger is a sensory instrument, not simply a tool for gripping. Your skin is packed with nerve endings called nociceptors, your pain detectors. These are your body's dedicated alarm system, firing only when tissue is damaged. But nociceptors are not spread evenly across the surface of your body. Fingertips pack roughly 2,500 touch-sensitive nerve endings per square centimeter. Your fingertips carry some of the densest touch and pain sensors anywhere. Your back has far fewer, which is why a back scratch feels vague. But a fingertip can detect a single grain of sand rolling across it. In the 1930s, Penfield mapped the sensory brain during awake surgeries. He built a strange diagram he called the sensory homunculus. It is a body map drawn by how much brain space each part commands. In it, the hands are drawn enormous, huge, and wildly exaggerated. The fingers claim a hugely outsized share of your brain's sensory cortex. So when a fingertip is hurt, a large brain region lights up. Under a microscope, the edge of paper is not smooth at all. Its edge is jagged, torn, and ragged, almost like a tiny saw. It does not slice cleanly. Instead, it shreds and tears the skin. A knife makes one clean cut. Paper makes chaos across the tissue. That ragged wound leaves far more nerve endings exposed and irritated. Paper cuts usually land on fingers, lips, and the tongue. These are the exact places carrying the most pain sensors of all. Location plus damage combine into a nearly perfect storm of pain. Paper cuts are shallow, striking only the upper layers of your skin. And that shallow zone is exactly where sensory nerves crowd together. A deeper cut passes right through them. A paper cut lingers among them. The wound stays open and unsealed, sitting right at the nerve layer. The fingertip epidermis measures roughly 0.5 to 1.5 millimeters thick. So the cut sits perfectly at the crowded alarm level of your skin. Deep cuts bleed heavily, and that blood quickly forms a protective clot. That clot becomes a scab, physically sealing the raw nerves away. Paper cuts barely bleed, so almost no protective seal ever forms. The nerves stay exposed to air, movement, and every tiny bump you make. Every time you bend that finger, the wound edges pull apart again. And your fingers are constantly working, typing, grabbing, and touching everything. Each motion reopens the raw edges and re-triggers the pain signal. Dermatologist Haley Goldbach notes that fingertips carry a dense supply of sensory neurons. The fingertip's cortical magnification factor, or CMF, is unusually large. Cortical magnification means small skin areas map onto large brain regions. You thought the pain was the injury. It is mostly amplification. The cut is trivial. Your brain simply devotes enormous attention to it. The same wound on your back would barely register as a passing itch. Pain is not a measure of damage. It is a measure of attention. Your fingertips evolved to feel everything, and that gift has a cost. Keeping the cut clean and covered can help calm the exposed nerves. A bandage restores the seal that the bleeding never managed to form. Next time a paper cut makes you gasp, remember what is really happening. It is not the paper hurting you. It is your brilliant, overprotective brain.